Today we're going to talk about conductors. So I have here, just as a rough experimental setup, some parallel plates that have been charged up with an equal amount of positive and negative charge. And I want to take some conducting material and I'm going to put it between those two plates. When I do that, what you'll see, again, we're just going to keep the same amount of positive charge. We're going to fix the positive and negative charges on those plates. They're going to stay glued to those plates. But now, I've got some conducting material that I've put in the middle of that. Well, by definition, electrical conductors have charges inside that can move around in response to an electric field. So originally, right when I put this slab of metal into the plates, right before I put it in there, there was an electric field pointing down like this. However, if there's an electric field inside the conductor, the charges are going to move around. And in fact, they're going to keep moving around until that electric field is no more. So what's going to happen is that my conductor is going to try to create an electric field in the opposite direction. Those two electric fields are going to exactly cancel out. Exactly cancel each other out. So there's going to be no electric field inside the conductor. There can be electric field outside the conductor, but inside the conductor there's no electric field. Let's go back to our rules for electric field. We know that electric field lines they come out of a positive charge and enter a negative charge. And all that's happening here is we've had some positive charges from the plate build up on the bottom side and some negative charges build up on the top plate. And they exactly cancel out the electric field that was coming from the original plate setup. So conductors, we figured out a few things for them. One of which is that the charges can flow inside. The other of which is that there can be no electric field inside the conductors. If there were, the charges would move around very, very quickly until there was no electric field, because as soon as you put an electric field, it's going to push the charges inside. Here are some observations that we can make about our little thought experiment with conductors. As we mentioned, the electric field inside a conductor is going to be zero at equilibrium. By equilibrium, all I mean is that the charges have had enough time to settle down so that any electric field that had made the charges moved is now canceled out because the charges have moved into a configuration where there will be no more electric field and no more pushing force on the charges. So basically, the charges move around until they cancel out the electric field. So we've seen that. Another thing we'll notice is that all charge lies on the surface. All charge lies on the surface. We know that this has to be true because if I had a charge somewhere in the middle, that charge would have to give an electric field, and we know that electric fields can't exist inside a conductor at equilibrium. So any charge that you do have has to be on the surface. The third rule that we can see, it might seem like it's only true for this geometry, but it will generally be true, is that the electric field lines are perpendicular to the surface of the conductor. They would have to be perpendicular because if they had any component along the direction of the conductor, let's just make a quick diagram of what that means. Suppose here's your conductor, and suppose the electric field was pointing at an angle. Suppose it was not perpendicular. Well, if there's some angle, what that means is that any charges that are on the surface are going to get pushed in that direction of the electric field. Because my electric field can be broken into a y component and an x component. And the x component of that electric field will push charges along the surface until there's no more x component of the electric field. So any charges that are on the surface are going to conspire, they're going to move around to make sure that the electric field is perpendicular to that surface. Another point that I will make suppose we have an odd-shaped conductor. Suppose it's teardrop shaped. Suppose I put charge on that electrical conductor. Well, the electric charge is going to go into different spots, but it turns out we're going to get more charge at the sharp points. Why do we get more charge at the sharp points? Well, those charges are all repelling each other. They're going to keep repelling each other until they find some stable configuration where there's no electric field inside the conductor. But the upshot of that is these charges want to get as far away from each other as possible. They want to get as far away from each other as possible. The furthest spot that you can get away is going to be on a sharp point. So we can say that charge concentrates at sharp points. Finally, the last thing I will say about general trends that we can notice for electric fields and potential inside conductors is that conductors are equipotentials. Why are conductors equipotentials? Well, suppose I have a conductor here, and suppose it was not an equipotential. Suppose, let's say, this half of the conductor had a potential of 100 volts, and this side of the conductor had a potential of 0 volts. Well, we know that if there is a difference in voltage, we showed before, when we were talking about potential energy, that whenever you have a difference in voltage, you have electric fields going from high voltage to low voltage. So if we have a difference in potential, that would mean that we'd have to have some electric field over some distance. So the difference between these two points times the electric field would have to be equal to the potential. We don't want that. That's bad, because that gives us an electric field inside our conductor. So since I can't have an electric field inside the conductor, I can't have any potential difference in the conductor. Therefore, conductors have to be equipotentials. At least at equilibrium, you cannot have a potential difference across a pure conductor. Now, I should throw the caveat out that this works for perfect conductors. No real material is quite a perfect conductor. But as long as it's good enough that we can approximate it as being a perfect conductor, all of these rules must hold. So we can't have electric fields inside. Any charges we do have on the conductor have to be on the surface. The electric field is going to be perpendicular to the surface. Charges concentrate at sharp points. And finally, the conductors have to be equipotentials. Today we're going to leave the world of electrostatics and move back into the world of circuits. And I'm going to start by doing just a little bit of a review for some of the things that we covered last semester. So one of the things we started with was talking about batteries. But we never really discussed how batteries work or how they were discovered or invented. And like many scientific discoveries, it started with a bit of an accident. So there was a man named Alessandro Volta, and once upon a time, he discovered that if you take two pieces of metal and connect them by a salt bridge, let's say this is metal number 1, this is metal number 2, and you connect them by a salt bridge, I'll say salt solution here. Then what you find is that you can actually have electric current flowing from one piece of metal to the other. So this could be copper, this could be zinc or some other metal. And potentially you could use that to light up a light bulb or do some other electrical bit of activity. Now that seems like an odd experiment just to try by happenstance. So how did Volta come up with this? Well, it turns out, no idea if this story is true, but it's what I've been told, that Volta basically just took two pieces of metal and was chewing on them. So if you stick two pieces of metal in your mouth, it turns out you have a very good salt bridge. It's also known as your tongue. And he noticed that when he did this, he got this tingling sensation. Presumably because there's some voltage difference there and probably some small amount of current that's flowing back and forth between the metals. So however it happened to be discovered, whether this is real or fake, now we know that there's an electric potential difference due to some bit of chemistry. Now we're not going to go deep into the chemistry of that. If you want to learn more about it, I recommend talking to any of the other chemistry professors that you have. But we are going to go and use this knowledge to go further and work with batteries and build electrical circuits. So let's say you take a battery and you connect that via some wires to some material. Well, if you do, and that material has a reasonably large conductivity, what you will find is that you get an electric current, which we give the symbol I. And the current, as we said last term, was just equal to delta Q over delta T, so it's how much charge is passing throughout the circuit. Now, remember we said that the current is kind of like a giant conga line of charges, all one right after the other. And the magnitude of the current, so that current is just circulating around. So the magnitude of the current starts everywhere at once. As soon as you flip a switch, connect the battery, all that big conga line is just going around, and the charges in front, so the current starts everywhere in the circuit all at once. So the conga line just kind of goes down along the line. But we don't have to worry about the charge leaving from the battery and getting all the way to the resistor. If we had to wait for the charge to get from the battery to the resistor, that would take a very long time because it turns out charges don't actually move that quickly on average. They're kind of bouncing around quite a bit inside the circuit. But fortunately, there are charges everywhere throughout the circle via the current loop that all start moving at once. So as soon as we connect the battery, the current starts flowing everywhere, and whatever this happens to be, if it's a light bulb or your computer or whatever piece of electrical equipment it is, it turns on almost immediately. That's how the current works. We also talked about resistance, and we said that if my battery has a certain voltage and my object has a certain resistance, and the resistance tries as much as it can to prevent the current from flowing. But whatever voltage difference we apply across the battery, that will determine how much current we get out. Actually, I'm going to write it this way. Let me change this up just ever so slightly. The current we're going to get out will be bigger if we apply a bigger voltage battery, and smaller if we have more resistance. So we can write a law that looks like this. This is called Ohm's law, which relates the current, resistance, and the voltage applied, or rather the voltage drop across a resistor. Now that we've reviewed a little bit what goes on in circuits, I want to expand on that, because there's going to be two questions we want to answer about circuits. The first question is, where are the charges going? In other words, what's the current? Is there any places where the charges get stuck, etc., etc.? So where are the charges going? The other question is, what is the energy doing? Are we losing energy? Are we using it in some important way? What's happening to the energy flowing in the circuit? So we want to know where the charges go and where the energy goes. To know where the energy goes, we want to figure out the power in this circuit. So how much energy does my battery lose every second? That's going to be the power. So the power for the battery, also known as an electromotive force, this is going to be the power used up from the battery, is going to be given by the current times the electromotive force. We'll say the voltage across the battery is just equal to some electromotive force. So this is the power, the rate at which energy gets used up inside a battery. Where does that energy go? Well, presumably it's getting dissipated in my resistor. Now, the resistor could be some light bulb. So the light bulb could be emitting energy in the form of electromagnetic waves, in the form of light. It could be heating up, so it could be releasing thermal energy. But energy should be conserved, and whatever energy the battery loses should be disseminated in some way by the resistor in the circuit. So we can look at the power used up by the resistor, and we have a few different ways of writing the power consumed by the resistor. I can write it as the current times the voltage drop across the resistor, which is pretty much the same formula as we got for the battery. I can write it using Ohm's law, just plugging in that the voltage drop across the resistor is the current times the resistance. That would give us I squared R. And finally, again using Ohm's law, if I want to replace the current rather than the resistance, we would get the voltage drop across the resistor squared divided by the resistance. So this is the rate at which energy is consumed inside a resistor. We can roughly relate that to how bright a light bulb is going to be, which is why the more current a light bulb gets, the brighter it's going to be.